This is how intelligence is made. A new kind of factory. Generator of tokens. The building blocks of AI. Tokens have opened a new frontier. The first step into an extraordinary world where endless possibilities are born. Tokens transform images into scientific data, charting alien atmospheres and guiding the explorers of tomorrow. They probe the Earth's depths to seek out hidden danger. They turn potential into plenty. And help us harvest our bounty. Tokens see disease before it takes hold. Cure with precision. And learn what makes us tick. Tokens connect the dots so we can protect our most noble creatures. Tokens decode the laws of physics to move us faster. And make our days more efficient. Tokens don't just teach robots how to move, but to bring joy and comfort.
Hi, Maroka. Hi, Anna. Are you ready to see the doctor? What's that? It's my enchanted tool.
Tokens help us move forward. One small step for man becomes one giant leap for mankind, so we can boldly go where no one has gone before. And here is where it all begins.
Stage, NVIDIA founder and CEO, Jensen Huang.
Hello, Paris! Bonjour! NVIDIA's first GTC in Paris. This is incredible. Thank you for all the partners that are here with us. We have so many people that we work with over the years. In fact, we've been in Europe for a very long time. Even though this is my first GTC Paris, I have a lot to tell you. NVIDIA, once upon a time, wanted to create a new computing platform to do things that normal computers cannot. We accelerated the CPU, created a new type of computing called accelerated computing, and one of our first applications was molecular dynamics. We've come a long way since. So many different libraries, and in fact, what makes accelerated computing special is it's not just a new processor that you compile software to. You have to reformulate how you do computing. You have to reformulate your algorithm. And it turns out to be incredibly hard for people to reformulate software and algorithms to be highly parallelized. And so we created libraries to help each market, each domain of application, become accelerated. Each one of these libraries opens up new opportunities for the developers, and it opens up new opportunities for growth for us and our ecosystem partners. Computational lithography, probably the single most important applications in semiconductor design today, runs in a factory at TSMC, Samsung, large semiconductor fabs. Before the chip is made, it runs through an inverse physics algorithm called cuLitho, computational lithography. Direct sparse solvers, algebraic multi-grid solvers. cuOpt, we just open sourced, incredibly exciting application library. This library accelerates decision-making to optimize problems with millions of variables for millions of constraints, like traveling salespeople problems. Warp, a Pythonic framework for expressing geometry and physics solvers, really important. cuDF, cuML, structured databases, data frames, classical machine learning algorithms. cuDF accelerates Spark, 0 lines of code change. cuML accelerates scikit-learn, 0 lines of code change. Dynamo and cuDNN. cuDNN is probably the single most important library NVIDIA has ever created. It accelerates the primitives of deep neural networks. And Dynamo is our brand new library that makes it possible to dispatch, orchestrate, distribute extremely complex inference workloads across an entire AI factory. Equivariance and cuTensor, tensor contraction algorithms. Equivariance is for neural networks that obey the laws of geometry, such as proteins, molecules. Ariel and Shiona, really important framework to enable AI to run 6G. Earth-2, our simulation environment for foundation models of weather and climate models. Kilometer square, incredibly high resolution. MONAI, our framework for medical imaging, incredibly popular. Parabricks, our solver for genomics analysis, incredibly successful. cuQuantum, CUDA-Q, I'll talk about in just a second, for quantum computing, and cuPyNumeric, acceleration for NumPy and SciPy. As you could see, these are just a few of the examples of libraries. There are 400 others. Each one of them accelerates a domain of application. Each one of them opens up new opportunities. Well, one of the most exciting is CUDA-Q. CUDA-X is this suite of libraries, a library suite for accelerating applications and algorithms on top of CUDA. We now have CUDA-Q. CUDA-Q is for quantum computing, for classical quantum classical computing based on GPUs. We've been working on CUDA-Q now for several years, and today I can tell you there's an inflection point happening in quantum computing. As you know, the first physical qubit was demonstrated some nearly 30 years ago. An error correction algorithm was invented in 1995. And in 2023, almost 30 years later, the world's first logical qubit was demonstrated by Google. Now, since then, a couple of years later, the number of logical qubits, which is represented by a whole lot of physical qubits with error correction, the number of logical qubits are starting to grow. Well, just like Moore's Law would, I could totally expect 10 times more logical qubits every 5 years, 100 times more logical qubits every 10 years. Those logical qubits would become better error corrected, more robust, higher performance, more resilient, and of course, will continue to be scalable. Quantum computing is reaching an inflection point. We've been working with quantum computing companies all over the world in several different ways, but here in Europe, there's a large community. I saw Pascal last night. I saw Barcelona supercomputing last night. It is clear now we're within reach of being able to apply quantum computing, quantum classical computing in areas that can solve some interesting problems in the coming years. This is a really exciting time. And so we've been working with all of the supercomputing centers. It's very clear now that over the next several years, or at least the next generation of supercomputers, every single one of them will have a QPU assigned and QPU connected to GPUs. The QPU will do quantum computing, of course, and the GPUs would be used for pre-processing, for control, for error correction, which will be intensely computationally intensive, post-processing and such. Between the two architectures, just as we accelerated the CPU, now there's QPU working with the GPU to enable the next generation of computing. Well, today we're announcing that our entire quantum algorithm stack is now accelerated on Grace Blackwell 200, and the speed up is utterly incredible. We work with the quantum computing industry in several different ways. One way is using cuQuantum to simulate the qubits or simulate the algorithms that runs on top of these quantum computers, essentially using a classical computer to simulate or emulate a quantum computer. At the other extreme, extremely important is CUDA-Q, basically inventing a new CUDA that extends CUDA into quantum classical, so that applications that are developed on CUDA-Q can run before the quantum computer arrives in an emulated way, or after the quantum computer arrives in a collaborative way, a quantum classical accelerated computing approach. And so today we're announcing CUDA-Q is available for Grace Blackwell. The ecosystem here is incredibly rich. And of course, Europe is deep with science and deep with supercomputing expertise and deep with heritage in this area. You might be surprised that I would be talking to you about AI. The same GPU that ran and enabled all of these applications that I mentioned, that same GPU enabled artificial intelligence to come to the world. Our first contact was in 2012, just prior to that, working with developers on a new type of algorithm called deep learning. It enabled the AlexNet big bang of AI, 2012. In the last 15 years or so, AI has progressed incredibly fast. The first wave of AI was perception, for computers to recognize information, understand it. The second wave, which most of us were talking about the last 5 years or so, was generative AI. It's multimodal, meaning that an AI was able to learn both images and language. Therefore, you could prompt it with language and it could generate images. The ability for AI to be multimodal, as well as able to translate and generate content, enabled generative AI revolution. Generative AI, the ability to generate content, is fundamentally vital for us to be productive. Well, we are starting a new wave of AI. In this last couple of years, we've seen enormous progress in AI's ability. Fundamentally, intelligence is about understanding, perception, reasoning, planning a task, how to solve a problem, and then executing the task. Perception, reasoning, planning, the fundamental cycles of intelligence. It allows us to apply some previously learned rules to solve problems we've never seen before. That's why intelligent people are considered intelligent. To be able to take a complicated problem, break it down step by step, reason about how to solve the problem, maybe do research, maybe go learn some new information, get some help, use tools, and solve problems step by step. Well, the words that I just described are fundamentally possible today with what is called agentic AI, and I'll show you more in just a second. In the physical implementation of that, the embodiment of that agentic AI, and the motion, now the generative capability is generating motion. Instead of generating videos and generating images or generating text, this AI generates locomotion, the ability to walk or reach out and grab something, use tools. The ability for AI to be embodied in a physical form is basically robotics. These capabilities, the fundamental technology to enable agents, which are basically information robots, and embodied AI, physical robots, these two fundamental capabilities are now upon us. Really, really exciting times for AI. But it all started with GeForce. And GeForce brought computer graphics. This is the first accelerated computing application we had ever worked on. And it's incredible how far computer graphics has come. GeForce brought CUDA to the world, which enabled machine learning researchers and AI researchers to advance deep learning. Then deep learning revolutionized computer graphics and made it possible for us to bring computer graphics to a whole new level. Everything I'm going to show you today, I'm going to give you a preview of what I'm going to show you, but everything I'm going to show you today is computer simulation, not animation. It's photon simulation, physics simulation, particle simulations. Everything is fundamentally simulation, not animation, not art. It just looks incredibly beautiful because it turns out the world is beautiful, and it turns out math is beautiful. So let's take a look.
I've got a cramp coming on. Oh, I can feel it.
What do you think? Numbers in action, numbers in action. That's essentially what simulations are, and it's just incredibly beautiful to look at. But because of the scale and the speed by which we can now simulate almost everything, we can turn everything into a digital twin. And because everything can be a digital twin, it can be designed, planned, optimized, and operated completely digitally before we put it into the physical world. The idea that we would build everything in software is now upon us. Everything physical will be built digitally. Everything that's built magnificently will be built digitally. Everything that's operated at gigantic scale will be first built digitally, and there will be digital twins that operate it. And so today we're going to talk a lot about digital twins. Well, what started out as a GeForce graphics card, anybody in here know what a GeForce is? Okay, all right. Well, what started out as GeForce looks like this now. This is the new GeForce. It is 2 tons, 2.5 tons, 1.2 million parts, about $3 million. 120 kilowatts, manufactured in 150 factories. 200 technology partners working with us to do this. Probably something along the lines of $40 billion in R&D budget in order to create what is GB200, and now moving to GB300. It is completely in production. And the machine was designed to be a thinking machine. A thinking machine in the sense that it reasons, it plans, it spends a lot of time talking to itself, just like you do. We spend most of our time generating words for our own mind, generating images for our own mind before we produce it. And so the thinking machine is really architecturally what Grace Blackwell was designed to do. It was designed to be one giant GPU. I compared it to GeForce for a good reason. GeForce is one GPU. So is GB200. It is one giant virtual GPU. Now we had to disaggregate it into a whole bunch of components, create a bunch of new networking technology and SerDes technology, incredibly low power, high energy efficiency interconnects to connect all of these chips and systems together into one virtual GPU. This is the Hopper version. This is the world famous Hopper system. This 8 GPUs connected together on NVLink. What's not shown here is a CPU tray. A CPU tray with dual CPU and system memory that sits on top. Together, this represents one node of an AI supercomputer. About $500,000. This is the Hopper system. This is the system that really put us on the face of the map of AI. And it was under allocation for a very long time because the market took off so quickly. But this is the famous Hopper system. Well, this entire system, including the CPU, is replaced by this Grace Blackwell node. This is one compute tray. Right here will replace that entire system. It is fully liquid cooled, and the CPUs are integrated directly connected to the GPUs. So you could see it here, 2 CPUs, 4 GPUs. Is more performant than that entire system. But what's amazing is this. We wanted to connect a whole bunch of these systems together. How would you connect all of these together was really hard for us to imagine. So we disaggregated it. What we did was we took that entire motherboard, we disaggregated into this and this. This is the revolutionary NVLink system. Scaling out computing is not that hard. Just connect more CPUs with Ethernet. Scaling out is not hard. Scaling up is incredibly hard. You can only build as large of a computer as you can build. The amount of technology and electronics that you could fit into one memory model is incredibly hard to do. And so what we decided to do was we created a new interconnect called NVLink. NVLink is a memory semantics interconnect. It's a compute fabric, not a network. It directly connects to the CPUs of all of these different NVLink systems, compute nodes. This is the switch. 9 of these stands on top. 9 of it sits on the bottom. In the middle are the NVLink switches. And what connects it together is this miracle. This is the NVLink spine. This is 100% copper. Copper coax. It directly connects all of the NVLink chips to all of the GPUs, directly connected over this entire spine, so that every single 144 Blackwell dies, or in 72 different packages, are talking to each other at the same time without blocking, all across this NVLink spine. The bandwidth of this is about 130 terabytes per second. 132, I know. No, wait for it. Wait for it. 130 terabytes per second. If it's in bits, 130 terabytes per second. It is more than the data rate of the peak traffic of the world's entire internet traffic on this backplane. And yeah. So this is how you shrink the internet into 60 pounds. NVLink. And so we did all that. We did all that because the way a computer is considered, the way you think about computers is going to be fundamentally different in the future, and I'll spend more time on this. But it was designed to give Blackwell a giant leap above Hopper. Remember, Moore's law, semiconductor physics, is only giving you about 2 times more performance every 3 to 5 years. How could we achieve 30, 40 times more performance in just one generation? And we need a 30, 40 times more performance because the reasoning models are talking to themselves. Instead of one-shot ChatGPT, it's now a reasoning model, and it generates a ton more tokens when you're thinking to yourself. You're breaking the problem down step by step. You're reasoning. You're trying a whole bunch of different paths. Maybe it's chain of thoughts. Maybe it's tree of thoughts, best of n. It's reflecting on its own answers. You've probably seen these research models reflecting on the answers, saying, is this a good answer? Can you do better than that? And they, oh yeah, I can do better than that. Goes back and thinks some more. And so those thinking models, reasoning models, achieved incredible performance, but it requires a lot more computational capability. And what net result, NVLink 72, Blackwell's architecture, resulted in a giant leap in performance. The way to read this is the x-axis is how fast it's thinking. The y-axis is how much the factory can output supporting a whole bunch of users at one time. And so you want the throughput of the factory to be as high as possible so you could support as many people as possible so that the revenues of your factory is as high as possible. You want this axis to be as large as possible because the AI is smarter here than it is here. The faster it can think, the more it can think before it answers your answer. And so this has to do with the ASP of the average selling price of the tokens, and this has to do with the throughput of the factories. These two combined in that corner is the revenues of the factory. This factory, based on Blackwell, can generate a ton more revenues as a result of the architecture. It is such an incredible thing what we built. We made a movie for you just to give you a sense of the enormity of the engineering that went into building Grace Blackwell. Take a look.
Blackwell is an engineering marvel. It begins as a blank silicon wafer. Hundreds of chip processing and ultraviolet lithography steps build up each of the 200 billion transistors, layer by layer on a 12-inch wafer. The wafer is scribed into individual Blackwell die, tested and sorted, separating the good dies to move forward. The chip-on-wafer on substrate process attaches 32 Blackwell dies and 128 HBM stacks on a custom silicon interposer wafer. Metal interconnect traces are etched directly into it, connecting Blackwell GPUs and HBM stacks into each system and package unit, locking everything into place. Then the assembly is baked, molded, and cured, creating the Blackwell B200 superchip. Each Blackwell is stress tested in ovens at 125 degrees Celsius and pushed to its limits for several hours. Robots work around the clock to pick and place over 10,000 components onto the Grace Blackwell PCB. Meanwhile, custom liquid cooling copper blocks are prepared to keep the chips at optimal temperatures. At At another facility, Connect X7 SuperNICs are built to enable scale-out communications, and Bluefield 3 DPUs to offload and accelerate networking, storage, and security tasks. All these parts converge to be carefully integrated into GB200 compute trays. NVLink is the breakthrough high-speed link that NVIDIA invented to connect multiple GPUs and scale up into a massive virtual GPU. The NVLink switch tray is constructed with NVLink switch chips, providing 14.4 terabytes per second of all-to-all bandwidth. NVLink spines form a custom blind-mated backplane with 5,000 copper cables connecting all 72 Blackwells, or 144 GPU dies, into one giant GPU, delivering 130 terabytes per second of all-to-all bandwidth, more than the global internet's peak traffic. From around the world, parts arrive to be assembled by skilled technicians into a rack-scale AI supercomputer. In total, 1.2 million components, 2 miles of copper cable, 130 trillion transistors, weighing nearly 2 tons. Blackwell is more than a technological wonder. It's a testament to the power of global collaboration and innovation, fueling the discoveries and solutions that will shape our future everywhere. We are driven to enable the geniuses of our time to do their life's work, and we can't wait to see the breakthroughs you deliver.
Grace Blackwell systems, all in production. It is really a miracle. It's a miracle from a technology perspective, but the supply chain that came together to build these GB200 systems, 2 tons each, we're producing them now, 1,000 systems a week. No one has ever produced, mass-produced supercomputers at this scale before. Each one of these racks is essentially an entire supercomputer. Only in 2018, the largest Volta system, the Sierra supercomputer in 2018, is less performant than one of these racks. And that system was 10 megawatts. This is 100 kilowatts. So the difference generationally between 2018 and now, we've really taken supercomputing, AI supercomputing to a whole new level, and we're now producing these machinery at enormous scales. And this is just the beginning. In fact, what you've seen is just one system, Grace Blackwell. The entire world is talking about this one system, clamoring for it to get deployed into the world's data centers for training and inferencing and generative AI. However, not everybody and not every data center can handle these liquid-cooled systems. Some data centers require enterprise stacks, the ability to run Linux Red Hat, or Nutanix, or VMware. Storage systems from Dell EMC, Hitachi, NetApp, VAST, Weka. So many different storage systems, so many different IT systems, and the management of those has to be done in the way that's consistent with traditional IT systems. We have so many new computers to ramp into production, and I'm so happy to tell you that every single one of these are now in production. You haven't seen them yet. They're all flying off the shelves, flying off the ramps, the manufacturing lines, starting here. DGX Spark enables you to have essentially the Grace Blackwell system on your desktop. In the case of Spark, desktop. In the case of DGX Station, desk side. This way, you don't have to sit on a supercomputer while you're developing your software, while you're developing your AI. But you want the architecture to be exactly the same. These systems are identical from an architecture perspective. From a software developer's perspective, it looks exactly the same. The only difference is scale and speed. And then on this side are all the x86 systems. The world's IT organization still prefers x86 and appreciates x86. Wherever they can take advantage of the most advanced AI native systems, they do. Where they can't and they want to integrate into the enterprise IT systems, we now offer them the ability to do so. One of the most important systems, and it's taken us the longest to build because the software and the architecture is so complicated, is how to bring the AI native architecture and infuse it into the traditional enterprise IT system. This is our brand new RTX Pro server. This is an incredible system. The motherboard is completely redesigned. Ladies and gentlemen, Janine Paul. This motherboard looks so simple, and yet on top of this motherboard are 8 Super NIC switches that connect 8 GPUs across a 200 gigabits per second state-of-the-art networking chip that then connects 8 of these GPUs and these Blackwell RTX Pro 6000 GPUs, brand new, just entered into production. 8 of these go into a server. Now, what makes it special? This server is the only server in the world that runs everything the world has ever written and everything NVIDIA has ever developed. It runs AI, Omniverse, RTX for video games, it runs Windows, it runs Linux, it runs Kubernetes and VMware. It runs basically everything. If you want to stream Windows desktop from a computer to your remote device, no problem. If you want to stream Omniverse, no problem. If you want to run your robotic stack, no problem. Just the QA of this particular machine is insane. The applications that it runs, basically universal. Everything the world's ever developed should run on here, including, if you're a video gamer, including Crysis. And so, if you can run Crysis, you can run anything. Okay, this is the RTX Pro server, brand new enterprise system. So something is changing. We know that AI is incredibly important technology. We know for a fact now that AI is software that could revolutionize, transform every industry. It can do these amazing things. That we know. We also know that the way you process AI is fundamentally different than the way we used to process software written by hand. Machine learning software is developed differently and it runs differently. The architecture of the systems, the architecture of the software, completely different. The way the networking works, completely different. The way it accesses storage, completely different. So we know that the technology can do different things, incredible things. It's intelligent. We also know that it's developed in a fundamentally different way. It needs new computers. The thing that's really interesting is, what does this all mean to countries, to companies, to society? And this is an observation that we made almost a decade ago that now everyone is awakening to. That in fact, these AI data centers are not data centers at all. They're not data centers in the classical sense of a data center, storing your files that you retrieve. These data centers are not storing our files. It has one job and one job only: to produce intelligent tokens, the generation of AI. These factories of AI look like data centers in the sense that they have a lot of computers inside, but that's where everything breaks down. How it's designed, the scale at which it's manufactured or scaled, designed, and built, and how it's used, and how it's orchestrated and provisioned, operated, how you think about it. For example, nobody really thinks about their data center as a revenue-generating facility. I said something that everybody goes, yeah, I think you're right. Nobody ever thinks about a data center as a revenue-generating facility, but they think of their factories, their car factories, as revenue-generating facilities. And they can't wait to build another factory, because whenever you build a factory, revenue grows shortly after. You could build more things for more people. Those ideas are exactly the same ideas in these AI factories. They are revenue-generating facilities, and they are designed to manufacture tokens. And these tokens can be reformulated into productive intelligence for so many industries that AI factories are now part of a country's infrastructure, which is the reason why you see me running around the world talking to heads of states, because they all want to have AI factories. They all want AI to be part of their infrastructure. They want AI to be a growth manufacturing industry for them. And this is genuinely profound. And I think we're talking about, as a result of all that, a new industrial revolution, because every single industry is affected, and a new industry. Just as electricity became a new industry. At first, when it was described as a technology and demonstrated as a technology, it was understood as a technology, but then we understood that it's also a large industry. Then there's the information industry, which we now know as the internet. And both of them, because it affected so many industries, became part of infrastructure. We now have a new industry, an AI industry, and it's now part of the new infrastructure called intelligence infrastructure. Every country, every society, every company will depend on it. And you can see its scale. This is one that's being talked about a lot. This is Stargate. This doesn't look like a data center. It looks like a factory. This is 1 gigawatts. It will hold about 500,000 GPU dies and produce an enormous amount of intelligence that could be used by everybody. Well, Europe has now awakened to the importance of these AI factories, the importance of the AI infrastructure. And I'm so delighted to see so much activity here. This is European telcos building AI infrastructure with NVIDIA. This is the European cloud service providers building AI infrastructure with NVIDIA. And this is the European supercomputing centers building next generation AI supercomputers and infrastructure with NVIDIA. And this is just the beginning. This is in addition to what will come in the public clouds. This is in addition to the public clouds. So indigenous built AI infrastructure here in Europe by European companies for the European market. And then there's 20 more being planned. 20 more AI factories and several that are gigafactories. In total, in just 2 years, we will increase the amount of AI computing capacity in Europe by a factor of 10. And so the researchers, the startups, your AI shortage, your GPU shortage will be resolved for you soon. It's coming for you. Okay. Now we're partnering with each country to develop their ecosystem. And so we're building AI technology centers in seven different countries. And the goal of these AI technology centers is, one, to do collaborative research, to work with the startups, and also to build the ecosystem. Let me show you what an ecosystem looks like. In the UK, I was just there yesterday, the ecosystems are built on top of the NVIDIA stack. So for example, every single NVIDIA, as you know, NVIDIA is the only AI architecture that's available in every cloud. It's the only computing architecture, aside from x86, that's available everywhere. We partner with every cloud service provider. We accelerate applications from the most important software developers in the world, Siemens here in Europe, Cadence, Red Hat, ServiceNow. We've reinvented the computing stack. As you know, computing is not just a computer, but it's compute, networking, and storage. Each one of those layers, each one of those stacks has been reinvented. Great partnership with Cisco, who announced a brand new model yesterday at their conference based on NVIDIA, Dell, great partnerships, NetApp, Nutanix, whole bunch of great partnerships. As I mentioned earlier, the way you develop software has been fundamentally changed. It's no longer just write C program, compile C program, deliver C program. It's now DevOps, ML Ops, AI Ops. So that entire ecosystem is being reinvented, and we have ecosystem partners everywhere. And then, of course, solution integrators and providers who could then help every company integrate these capabilities. Well, here in the UK, we have special companies that we work with, really terrific companies, from researchers to developers to partners to help us upskill the local economy and upskill the local talent, enterprises that consume the technology, and of course, cloud service providers. We have great partners in the UK. We have great partners in Germany. Incredible, incredible partnerships in Germany. We have great partnerships in Italy. And we, of course, have amazing partnerships here in France. That's right, go France. President Macron's going to be here later on. We're going to talk about some new announcements. So we have to show some enthusiasm for AI, okay? Yeah. There you go. Show him some enthusiasm. So great partnerships here in France. One particular one I want to highlight, our partnership with Schneider, building these AI factories. We build them digitally now. We design them digitally, we build them digitally, we operate them or optimize them digitally, and we will even eventually optimize them and operate them completely digitally in a digital twin. These AI factories are so expensive, $50 billion sometimes, $100 billion in the future. If the utilization of that factory is not at its fullest, the cost to the factory owner is going to be incredible. And so we need to digitalize and use AI wherever we can, put everything into Omniverse so that we have direct and constant telemetry. We have a great partnership here that we're announcing today. A young company, a CEO I really like, and he's trying to build a European AI company. The name of the company is Mistral. Today we're announcing that we're going to build an AI cloud together here to deliver their models as well as deliver AI applications for the ecosystem of other AI startups so that they can use the Mistral models or any model that they like. And so Mistral and us, we're going to be partnering to build a very sizable AI cloud here, and we'll talk about more of it later on today with President Macron. AI technology is moving at light speed. And what I'm showing you here, proprietary models on the left, moving at light speed. However, the open models are also moving at light speed, only a few months behind. Whether it's Mistral, Llama, DeepSeek R1, R2 coming, Q1, these models are all exceptional. Every single one of them exceptional. And so we've dedicated ourselves over the last several years to apply some of the world's best AI researchers to make those AI models even better. And we call that Nemotron. Basically what we do is we take the models that are open sourced, and of course they're all built on NVIDIA anyhow, and so we take those models open sourced, we then post-train it. We might do neural architecture search. Provide it with even better data. Use reinforcement learning techniques. Enhance those models. Give it reasoning capabilities. Extend the context so that it could learn and read more before it interacts with you. Most of these models have relatively short context, and we want it to have enormous context capability because we want to use it in enterprise applications where the conversation we want to have with it is not available on the internet. It's available in our company. And so we have to load it up with an enormous amount of context. All of that capability is then packaged together into a downloadable NIM. You could come to NVIDIA's website and literally download an API, a state-of-the-art AI model. Put it anywhere you like. And we improve it tremendously. This is an example of Nemotron improvement over Llama. So Llama 8B, 70B, 405B, improved by our post-training capability, extension of reasoning capability, all the data that we provide, enhanced it tremendously. We're going to do this generation after generation after generation. And so for all of you who uses Nemotron, you will know that there's a whole slew of other models in the future, and they're open anyway. So if you would like to start from the open model, that's terrific. If you'd like to start with the Nemotron model, that's terrific. And the Nemotron models, the performance is excellent. In benchmarks after benchmarks after benchmarks, Nemotron performance has top of the leaderboard all over the place. And so now you know that you have access to a enhanced open model that is still open, that is top of the leader chart. And you know that NVIDIA is dedicated to this, and so I will do this for as long as I shall live, okay? This strategy is so good. This strategy is so good that the regional model makers, the model builders across Europe, have now recognized how wonderful this strategy is, and we're partnering together to adapt, enhance each one of those models for regional languages. Your data belongs to you. Your data belongs to you. It is the history of your people, the knowledge of your people, the culture of your people. It belongs to you. And for many companies, in the case of NVIDIA, our data is largely inside. 33 years of data. I was looking up this morning. Siemens, 180 years of data. Some of it written down on papyrus. Roland Bush is here. I thought I'd pick on Roland Bush, my good friend. And so you'll have to digitize that before the AI can learn. And so the data belongs to you. You should use that data, use an open model like Nemotron and all the tool suites that we provide so that you can enhance it for your own use. We're also announcing that we have a great partnership with Perplexity. Perplexity is a reasoning search engine. Yep. The three models I use ChatGPT, Gemini Pro, and Perplexity. And these three models I use interchangeably, and Perplexity is fantastic. We're announcing today that Perplexity will take these regional models and connect it right into Perplexity so that you could now ask and get questions in the language, in the culture, in the sensibility of your country. Okay, so Perplexity, regional models. Agentic AI. Agentic AI, agents, is a very big deal. As you know, in the beginning, with pre-trained models, people said, but it hallucinates. It makes things up. You're absolutely right. It doesn't have access to the latest news and data information. Absolutely right. It gives up without reasoning through problems. It's as if every single answer has to be memorized from the past. You're absolutely right. All of those things, you know, why is it trying to figure out how to add or count numbers and add numbers? Why doesn't it use a calculator? You're absolutely right. And so all of those capabilities associated with intelligence, everybody was able to criticize, but it was absolutely right because everybody largely understands how intelligence works. But those technologies were being built all around the world, and they were all coming together from retrieval augmented generation to web search to multimodal understanding so that you can read PDFs, go to a website, look at the images and the words, listen to the videos, watch the videos, and then take all of that understanding into your context. You could also now understand, of course, a prompt from almost anything. You could even say, I'm going to ask you a question, but start from this image. I could say, start from this text before you answer the question or do what I ask you to do. It then goes off and reasons and plans and evaluates itself. All of those capabilities are now integrated, and you can see it coming out into the marketplace all over the place. Agentic AI is real. Agentic AI is a giant step function from one-shot AI. The one-shot AI was necessary to lay the foundation so that we can teach the agents how to be agents. You need some basic understanding of knowledge and basic understanding of reasoning to even be able to be teachable. And so pre-training is about teachability of AI. Post-training, reinforcement learning, supervised learning, human demonstration, context provision, generative AI, all of that is coming together to formulate what is now agentic AI. Let's take a look at one example. Let me show you something. It's built on Perplexity, and it's super cool.
AI agents are digital assistants. Based on a prompt, they reason through and break down problems into multi-step plans. They use the proper tools, work with other agents, and use context from memory to properly execute the job on NVIDIA accelerated systems. It starts with a simple prompt. Let's ask Perplexity to help start a food truck in Paris. First, the Perplexity agent reasons through the prompt and forms a plan. Then, calls other agents to help tackle each step using many tools. The market researcher reads reviews and reports to uncover trends and analyze the competitive market. Based on this research, a concept designer explores local ingredients and proposes a menu complete with prep time estimates, and researches palettes and generates a brand identity. Then, the financial planner uses Monte Carlo simulations to forecast profitability and growth trajectory. An operations planner builds a launch timeline with every detail, from buying equipment to acquiring the right permits. The marketing specialist builds a launch plan with a social media campaign and even codes an interactive website, including a map, menu, and online ordering. Each agent's work comes together in a final package proposal, and it all started from a single prompt.
One prompt like that in the original chatbot would have generated a few hundred tokens. But now with that one single prompt into an agent to solve a problem, it must have generated 10,000 times more tokens. This is the reason why Grace Blackwell is necessary. This is the reason why we need performance in the systems to be so much more performant generationally. Well, this is how Perplexity builds their agents. Every company will have to build their own agents. It's terrific. You're going to be hiring agents from OpenAI and Gemini and Microsoft Copilot and Perplexity and Mistral, and there'll be agents that are built for you. And they might help you plan a vacation or, go do some research, so on and so forth. However, if you want to build a company, you're going to need specialized agents on specialized tools and using specialized tools and specialized skills. And so the question is, how do you build those agents? And so we created a platform for you. We created a framework and a set of tools that you can use and a whole bunch of partners to help you do it. It starts with, on the very bottom, the ability to have reasoning models that I spoke about. NVIDIA's Nemotron reasoning large language models are world-class. We have Nemo Retriever, which is a multimodal search engine, semantic search engine, incredible. And we built a blueprint, a demonstration that is operational, that is essentially a general agent. We call it IQ, AIQ. And on top, we have a suite of tools that allows you to onboard an agent, a general agent, curate data to teach it, evaluate it, guardrail it, supervise, train it, use reinforcement learning, all the way to deployment. Keep it secure, keep it safe. That suite of toolkits is integrated, those libraries are integrated into the AI ops ecosystem. You can come and download it from our website yourself as well, but it's largely integrated into AI ops ecosystem. From that, you could create your own special agents. Many companies are doing this. This is Cisco. They announced it yesterday. We're building AI platforms together for security. Now, look at this. AI agents are not one model that does all of these amazing things. It's a collection, a system of models. It's a system of AI large language models. Some of them are optimized for certain type of things. Retrieval, as I mentioned, performing skills, using a computer. You don't want to bundle all of that stuff up into one giant, mass of AI, but you break it up into small things that you could then deploy CI/CD over time. This is an example of Cisco's. Now the question is, how do you now deploy this? Because as I mentioned earlier, there are public clouds where NVIDIA's compute is. There are regional clouds, we call them NCPs. Here, for example, Mistral. You might have something that is private cloud because of your security requirements and your data privacy requirements. You might even decide that you have something on your desk. And so the question is, how do you run all of these? And sometimes they will run in different places because these are all microservices. These are AIs that could talk to each other. They could obviously talk to each other over networking. And so how do you deploy all of these microservices? Well, we now have a great system. I'm so happy to announce this for you. This is called our DGX Lepton. DGX Lepton, what you're looking at here, is a whole bunch of different clouds. Here's the Lambda cloud, the AWS cloud, here's your own developer's machine. Your own system could be a DGX station, Nebius, Yoda, and Scale. It could be AWS, it could be GCP. NVIDIA's architecture is everywhere. And so you could decide where you would like to run your models. You deploy it using one super cloud, so it's a cloud of clouds. Once you get it to work, once you get this NIMS deployed into Lepton, it will go and be hosted and run on the various clouds that you decide. One model architecture, one deployment, and you can run it everywhere. You can even run it on this little tiny machine here. This DGX Spark. Is it a cafe time? Look at this. This lift is 2,000 horsepower. This is my favorite little machine. DGX Spark. The AI supercomputer, we built an AI supercomputer in 2016. It's called the DGX-1. It was the first version of everything that I've been talking about. 8 Volta GPUs connected with NVLink. It took us billions of dollars to build. And on the day we announced it, DGX-1, there were no customers, no interest, no applause, 100% confusion. Why would somebody build a computer like that? Does it run Windows? Nope. And so we built it anyways. Well, thankfully, a young company, a startup, a nonprofit startup in San Francisco was so delighted to see the computer. They said, "Could we have one?" And I thought, oh my gosh, we sold one. But then I discovered it was a nonprofit. But I put a DGX-1 in my car, and I drove it up to San Francisco, and the name of that company is OpenAI. So I don't know what the life lesson is there. There are a lot of nonprofits, So next time, but maybe the lesson is this: if a developer reaches out to you and need a GPU, the answer is yes. And so that's right. So imagine you have Lepton. It's in your browser, and you have this Helm chart, an AI agent that you've developed, and you want to run it here. And parts of it you want to run in AWS, and parts of it you want to run, in a regional cloud somewhere. You use Lepton, you deploy your Helm chart, and it magically shows up here, okay? And so if you would like to run it here until you're done with and ready to deploy it, and then deploy it into the cloud, terrific. But the beautiful thing is this architecture is based on Grace Blackwell. GB10 versus GB200 versus GB300, and all of these different versions of, but this architecture is exactly Grace Blackwell. Now this is amazing. So we're doing this for Lepton, but next, Hugging Face and NVIDIA has connected Lepton together. And so whenever you're training a model on Hugging Face, if you would like to deploy it into Lepton and directly into Spark, no problem. It's just one click. So whether you're training or inferencing, we're now connected to Hugging Face, and Lepton will help you decide where you want to deploy it. Let's take a look at it.
Developers need easy and reliable access to compute that keeps up with their work. Wherever they are, for fast distributed inference. Just like ride-sharing apps connect riders to drivers, DGX Cloud Lepton connects developers to GPU compute, powering a virtual global AI factory.
DGX Cloud Lepton. Okay, so that's Cisco. This is the way SAP, they're building an AI platform in NVIDIA. Sana is building an AI business application automation on NVIDIA. DeepL is building their language framework and platform on NVIDIA AI. Photo Room, a video editing and AI editing platform, building their platform on NVIDIA. And this is Codo, used to be, I think, Codium, incredible coding agent built on NVIDIA. And this is Iola, a voice platform built on NVIDIA. And this one is a clinical trial platform, the world's largest automation platform for clinical trials built on NVIDIA. And so all of these basically builds on the same idea. NIMS that encapsulates and packages up in a virtual container that you could deploy anywhere, the Nemotron large language model, or other large language models like Mistral or others. We then integrate libraries that basically covers the entire life cycle of an AI agent. The way you treat an AI agent is a little bit like a digital employee. So your IT department would have to onboard them, fine-tune them, train them, evaluate them, keep them guardrailed, keep them secure, and continuously improve them. And that entire framework platform is called NEMO. And all of that is now being integrated into one application framework after another all over the world. This is just an example of a few of them. And then now we make it possible for you to deploy them anywhere. If you want to deploy it in the cloud, you got DGX, you got GB200s in the cloud. If you want to deploy it on-prem, because you've got VMware or Red Hat Linux or Nutanix, and you want to deploy it in your virtual machines on-prem, you can do that. If you want to deploy it as a private cloud, you could do that. You're going to deploy it all the way on your DGX Spark or DGX Station, no problem. And so Lepton will help you do all of that. Let's talk about industrial AI. This is one of my favorite moments. This is Roland Busch. this is a really fun moment. He wanted to remind me that neural network computers were invented in Europe. That's this whole slide. It was such a great moment. This is the Synapse 1. This is incredible, you guys. Synapse 1. This is Synapse 1, 1992. It runs neural networks 8,000 times faster than CPUs at that time. Isn't that incredible? So this is the world's AI computer. And Roland just wants to, never forget that, Jensen. Never, ever forget that. I said, okay, all right. I'll even tell everybody. Siemens 1992. Siemens 1992. We have a great partnership with Siemens, and Roland Busch, the CEO, is supercharging the company so that they could completely leap the last IT industrial revolution and fuse the industrial capabilities of Europe, the industrial capabilities and might of Siemens with artificial intelligence and create what is called the industrial AI revolution. We're partnering with Siemens on so many different fronts. Everything from design to simulation to digital twins of factories to operations of the AIs in the factories, everything from end to end. And it just reminds me how incredible the industrial capabilities of Europe is, and what an extraordinary opportunity this is for you. What an extraordinary opportunity, because AI is unlike software. AI is really, really smart software. And this smart software can finally do something that can revolutionize the very industries that you serve. And so we made a love letter video, if you will. Let's play it.
It began here. The first industrial revolution. Watt's steam engine and the mechanized loom introduced automation and the advent of factories, and industry was born. The age of electricity. Ampere unraveled electromagnetism. Faraday built the first electric generator, and Maxwell laid the foundations for modern electrical engineering. Siemens and Wheatstone's dynamo, the engine of electricity, bringing machines, trains, factories, and cities to life, electrifying the planet, igniting modern manufacturing. And today, born out of the computing and information age, the fourth industrial revolution, the age of AI, reimagining every part of industry. Across the continent, industrial AI is taking hold. From design to engineering, you're blazing new trails toward understanding and reinvention. You brought the physical world into the virtual to plan and optimize the world's modern factories. You're building the next frontier, where everything that moves is robotic. Every car, an intelligent autonomous agent, and a new collaborative workforce to help close the global labor shortage gap. Developers across the continent are building every type of robot, teaching them new skills in digital twin worlds and robot gyms, preparing them to work alongside us in our factories, warehouses, the operating room, and at home. The fourth industrial revolution is here, right where the first began.
What do you think? I love that video. You made it. That's so great. You made it. Well, we're working on industrial AI with one company after another. This is BMW building their next generation factory in Omniverse. This is, I don't know how to say it. Can somebody teach me? Bujes? Sounds good. Exactly. That's exactly right. Good job. Good job. That's exactly right. They're building, of course, their plants, digital twins in Omniverse. This is Kion, their digital twin for warehouse logistics. This is Mercedes-Benz and their digital twins of their factories built in Omniverse. This is Schaeffler and their digital twin of their warehouse built in Omniverse. This is your train station here in France, building a digital twin of their train stations in Omniverse. And this is Toyota building a digital twin of their warehouse in Omniverse. And when you build these warehouses and these factories in Omniverse, then you could design it, you can plan it, you can change it. In greenfield is wonderful, in brownfield is wonderful. You could simulate its effectiveness before you go and physically lift and move things around to discover it wasn't optimal. And so the ability to do everything digitally in a digital twin is incredible. But the question is, why does the digital twin has to look photoreal? And why does it have to obey the laws of physics? The reason for that is because we wanted ultimately to be a digital twin where a robot can learn how to operate as a robot. And robots rely on photons for their perception system. And those photons are generated through Omniverse. And robots needs to interact with the physical world so that it could know whether it's doing the right things and learn how to do it properly. And so these digital twins have to look real and behave realistically. Okay, so that's the reason why Omniverse was built. This is fantastic. This is a fusion reactor digital twin. Incredibly complicated piece of instrument, as you know, and without AI, the next generation fusion reactor would not be possible. Well, we're announcing today that we are going to build the world's first industrial AI cloud here in Europe. I'm going to announce, yep. These industrial AI clouds are, yes, whole lot of computers in the cloud. However, its requirement, its performance, its safety requirements fundamentally different. And so I'm going to tell you a lot more about it on Friday. I'm only teasing you part of the story today, but this industrial cloud will be used for design and simulation, virtual, and let robots learn how to be great robots and build the robots of our future, self-driving cars and such. We already have tremendous ecosystem here. We've been here, as you know, for a very long time. NVIDIA's 33 years old. The first time we came to Europe was during the time when workstations and the digitalization of products, CAD, the CAD revolution started. We were here doing the CAE revolution, and now the digital twin revolution. Some $2 trillion of ecosystem here in Europe that we partner with and that we have the privilege of supporting. What comes out of that is a new revolution that's happening. As you know, everything that moves will be robotics. Everything that moves will be AI driven. And the car is the most obvious next one. NVIDIA builds the AI supercomputers to train the model. The AI supercomputer for Omniverse digital twins. We also build the AI supercomputers for the robots itself. In every single case, whether it's in the cloud, for Omniverse, or in the car, we offer the entire stack. The computer itself, the operating system that runs on top of this computer, which is different in every single case. This computer, high speed, sensor rich, must be functional safe. In no circumstance could it fail completely. And so the safety requirements incredibly high. And now we have an incredible model that sits on top of it. This model that sits on top of it is a transformer model. It's a reasoning model, and it takes sensor in, you tell it what you want it to do, and it will drive you there. takes pixels in, and it generates path plans output. So it's a generative AI model based on transformers. Incredible technology. NVIDIA's AI team, AV team, is incredible. This is the only team that I know that has won end-to-end self-driving car challenge at CVPR 2 years in a row. And so they're the winner again this year. Let's take a look at the video. Yep, thank you.
Like any driver, autonomous vehicles operate in a world full of unpredictable and potentially safety-critical scenarios. NVIDIA Drive, built on the Halo safety system, lets developers build safe autonomous vehicles with diverse software stacks and sensors and redundant computers. It starts with training. Safe AVs need massive amounts of diverse data to be able to address edge cases. But real-world data is limited. Developers use NVIDIA Omniverse and Cosmos to reconstruct the real world and generate realistic synthetic training data to bring diversity to the AV model. The model can perceive and reason about its environment, predict future outcomes, and generate a motion plan. And for decision-making diversity, an independent classical stack runs in parallel. Guardrails monitor safe performance, and in cases of anomalies, calls the arbitrator to make an emergency stop. Further diversity and redundancy are built into the sensor and compute architecture. Each sensor connects to redundant computers. So even if a sensor or computer fails, the vehicle stays safe and operational. And in the event of a critical failure, the system can execute a minimum risk maneuver, like pulling over to the shoulder. Safety is foundational to autonomous driving. NVIDIA Drive lets developers worldwide integrate Halos into their own products to build the next generation of safe AVs.
A billion cars on the road, 10,000 miles a year on average, 10 trillion miles. The future of autonomous driving is obviously gigantic, and it's going to be powered by AI. This is the next gigantic opportunity, and we're working with enormous companies and really fantastic companies around the world to make this possible. At the core of everything we do here with AV is safety, and we're really, really proud of our Halo system. It starts with the architecture of the chip, and then the chip design, and the systems design, the operating system, the AI models, the methodology of developing the software, the way we test it, everything from the way we train the models, the data we provide for the models, all the way to the way we evaluate the models. NVIDIA's Halo system and our AV safety team and capabilities are absolutely world-renowned. This computer was the first one to be software-defined. The world's first software-defined, completely 100% software-defined AI-driven software, AI-driven stack for AVs. We've been at this now for coming up on 10 years. And so this capability is world-renowned, and I'm really proud of it. The same thing that's happening for cars is happening for a new industry. As I mentioned earlier, if you can generate video from prompts, if AI can perceive, it can reason, and it can generate videos and words and images, and just now with cars, the path, the steering wheel path, why can't it also generate locomotion abilities and articulation abilities? So that fundamental ability for AI to revolutionize one of the hardest robotics problems is around the corner. Humanoid robots are going to be a thing. We now know how to build these things, train these things, and operate these things. Humanoid robotics is going to potentially be one of the largest industries ever. And it requires companies who know how to manufacture things of extraordinary capabilities. This speaks of the European countries. So much of the world's industries are based here. I think this is going to be a giant opportunity. Well, let's say it's 1 billion robots around the world. The idea that there'll be 1 billion robots is a very sensible thing. Now, why hasn't it happened? Well, the reason for that is simple. Today's robots are too hard to program. Only the largest companies can afford to install a robot, get it to teach it, program it to do exactly the right things, keep it sufficiently surrounded so that it's safe. That's the reason why the world's largest car companies all have robots. They're large enough, the work is sufficiently repetitive, the industry is at a sufficient scale that you could deploy robots into those factories. Almost everybody who's a Mittelstand or small, medium companies or mom and pop restaurants or stores or warehouses, it's impossible to have that programming capability until now. We're going to give you essentially robots where you could teach them. They'll learn from you. Just as we were talking about agentic AI, we now have humanoid AI that can learn from your teaching using toolkits that are very consistent with the NEMO toolkits I spoke about. NVIDIA here as well is built in 3-layer stack. We build the computer, the Thor computer dev kit looks a little bit like this. This is a robotic computer, completely self-contained dev kit, sits on your desk. These are all the sensors. And inside is a little supercomputer Thor chip. Just really, really incredible.